Today we're diving into one of the most important relationships in physics: how force, mass, and acceleration are connected. This idea is used everywhere, from designing rockets and race cars to understanding how athletes throw, jump, and sprint. And once you understand it, the entire world of motion starts to make sense. Let's begin with acceleration. Acceleration simply tells us how quickly an object changes its velocity. If the velocity is changing, whether the object is speeding up, slowing down, or changing direction, then some net force must be acting. And that's the key word: net force. Not every force, only the leftover, unbalanced force. Imagine two different bows in archery: a simple bow that pulls with a force of about 150 newtons, and a compound bow that pulls with roughly 300 newtons. If both fire arrows of the same mass, which arrow will accelerate more? Obviously, the one pushed by the larger force. The relationship is straightforward. If the mass stays the same, more force means more acceleration. Double the net force, double the acceleration. Keep the mass constant, and acceleration depends directly on how hard you push. Now let's switch perspectives. Instead of changing the force, what happens if you keep the force the same, but change the mass? Picture two discus throwers using the same effort. One discus has a mass of 1 kilogram, and the other weighs 2 kilograms. Because the same force is being applied, the lighter discus accelerates more easily. That means the heavier an object is, the harder it is to accelerate. Acceleration decreases as mass increases. In other words, acceleration is inversely proportional to mass. So at this point, we've discovered two patterns: acceleration increases when force increases, and acceleration decreases when mass increases. But how do we combine these ideas into one relationship? To figure it out, scientists perform controlled experiments. Let's imagine one. You take a racing cart and apply 3 different forces to it: a small force, a medium one, and a larger one. You keep the mass the same. Each time, you measure the acceleration. You would get a smooth straight line graph. As the force goes up, the acceleration goes up at the same rate. That tells us force is directly proportional to acceleration when mass stays constant. Then you repeat the experiment differently. You keep the same force, but now you use carts of different masses: a light cart, a medium cart, and a heavy one. This time the graph curves downward. The bigger the mass, the smaller the acceleration. That tells us acceleration decreases as mass increases. When you put both results together, the complete relationship becomes beautifully simple. Acceleration equals net force divided by mass. This means if you want something to accelerate more, you must either increase the net force or reduce the mass. If the mass is large, like a rocket at liftoff, you need an enormous force just to get it off the ground. If the mass is small, like a sprinter's shoe or a tennis ball, a small force can produce a large acceleration. This relationship also explains why engineers are obsessed with reducing mass. Race cars are built with carbon fiber, cyclists wear lightweight helmets, and even smartphones are designed to be lighter so your hands can accelerate them easily. Lower mass means quicker response, and you've probably seen this relationship in everyday life without even realizing it. When you push an empty shopping cart, it moves instantly. Fill the cart with heavy boxes, and suddenly the same push produces way less acceleration. The push didn't change, but the mass did. When a soccer player kicks a light ball, it rockets forward. If the ball were twice as heavy, the same kick would barely move it. Everything around you follows the rule that acceleration depends on both how hard you push and how much mass you're trying to accelerate. Now let's combine this with what we know about forces. Because force is a vector, the acceleration is always in the same direction as the net force. If the net force points forward, the acceleration is forward. If the net force points upward, the acceleration is upward. And if all the forces cancel out, meaning the net force is 0, then the acceleration is 0. The object either stays still or keeps moving at constant velocity. So behind every change in motion, there is always a reason: a net external force. Behind every acceleration, there is a push or pull that isn't being canceled. Behind every slowdown, every curve, every launch, every sprint, there is an unbalanced force producing acceleration. Understanding the relationship between force, mass, and acceleration is not just about passing physics. It helps you understand how seatbelts protect you by applying a force that reduces your acceleration in a crash. It helps engineers design rockets that can lift massive loads. It explains how athletes optimize their movements, how machines operate, and how every object in the universe responds to forces. And remember, this entire idea was discovered through controlled experiments, careful measurements, and the simple observation that nature follows patterns. Once you see the pattern, the formula becomes obvious. Acceleration equals net force divided by mass. If you enjoyed learning this and want more simple, clear breakdowns of grade 11 physics, make sure to like this video and subscribe. It helps us grow the channel and bring you more educational content every week.